So please welcome Matti Pehrs.
Thank you. So today I'm going to talk a bit about our experience in scaling our data infrastructure at Spotify. Just a brief check. So how many of you guys work with big data today? So a fair bit. So, well, typically Hadoop. So when I talk about Hadoop stuff, you should know what I mean. So okay, let's start. So this is me. I've been around for quite some time. I love Emacs. I love Java. But what's kind of more interesting is that I've been with Spotify for the last 3.5 years, working in their data infrastructure. So a bit of agenda. We're going to start by talking about how we do big data or how we work with big data at Spotify, and a bit of history. Then we're going to move to the summer of 2015 and what happened there. And then we're going to go through some of the challenges that we had then and how we basically solved them by basically implementing these 3 systems that you see. So I'm going to go into the more details as we move along. So data at Spotify. So talking about big data, and good question there, what is big data? You know, you can't ignore the big elephant in the room. It's typically at the heart of any data infrastructure, it would be your Hadoop cluster. So let's take a look at our history with Hadoop. I mean, it's been 10 years now. We started in 2007 with just 5, actually, Debian build servers that we were running Hadoop on. And not everybody was so happy about that, because when you run Hadoop at full speed, the fans typically go off and makes a lot of noise. So we ended up creating a data center, and that's the sort of picture you see on the right. You see John there, who's super happy because the data center, which was incidentally also the foosball room, we had a problem with some of the servers crashing when we were processing data. And this is John when he realized why. Because at this point he had bought some curtains. So this room had a window, and there was sun out, and the sun hit the top servers, and they were overheating. So yeah, so that's sort of the beginnings of our big data with Hadoop. In 2010, we sort of started becoming a bit more serious with this. We started to move out of our office sort of data center, and we started to play with Elastic MapReduce. It didn't really fit us that well back then. Frankly, it was a bit too expensive for us at the time. But as we moved along, in 2012, we had grown to about, I would say, 200 nodes in our data center. And by this time, we were doing proper co-location in London. What happened in 2012 is interesting, because that's sort of the breaking point when big data started becoming really important for us, like business critical. It was sort of business critical, but now we just had so many data jobs that it actually was really critical. And that's when we started using Hortonworks, so basically a managed product, so we could actually get back ports of bugs and such, which actually becomes important. The other part was that we actually invested in hiring Hadoop experts. So instead of just doing this as a normal back-end engineer kind of thing, we actually hired people who were really into Hadoop and really wanted to tweak the sort of details of Hadoop. And that sort of was the starting point, and we started to grow really heavily from that. And of course, this grew, of course, with our data. And today, we are running a fairly big cluster in London with more than 2,000 nodes. And the big challenge here is that now we're running out of physical space. So the next step would be to find a bigger place or build a data center of our own. And we don't really want to do that. So we are moving to the cloud. And we are moving to the cloud with Google. Now you might ask, so why are we moving to the cloud now? And why are we doing this with Google? So from a big data perspective, it's all about focus. We are a music streaming company. We don't want to operate data centers. That That's not what we want to do. So moving to the cloud makes sense because this will just basically lessen that operational burden, and we can just scale without thinking about it. And why Google then? Well, if you look at the last 10 years, Google has been the dominating force in big data, basically inventing sort of MapReduce, that is sort of the basis of Hadoop. And they've been innovating in this area already for 10 years. And we believe that they will continue to do this. And Spotify is heavily invested in big data. We believe that that is the differentiator for us, for our product. So with the Google's help and their infrastructure, we believe that we can, focus on music streaming and music services rather than creating huge infrastructures. They already have it. I mean, we're running some 12,000 servers today in our data centers. Google has well over 1 million or something like that. So they're much better at that. Now let's move on to looking at a bit of the data context. So we have more than 100 million active users per month. We have a catalog of more than 30 million songs. But what's maybe more interesting is that we have more than 2 billion playlists generated by our users. And we're active in 60 different countries. Now this translates into a lot of data. So there's a sort of fake timeline here, but the interesting part here is that today, from our users, we're pretty much ingesting north of 50 terabytes of data every day. That's quite a lot of data. But what's more interesting is that our developers and our analysts are producing even more. And that's actually increasing typically at even a higher rate. So today it's around north of 60 terabytes of data every day. We're running some 10,000 MapReduce jobs per day. It varies a bit. And then if we look at how data is used at Spotify, I mean, if we backtrack to 2007, it was all about reporting. We needed to create these monthly reports to actually calculate how much songs were used so we could pay, the labels what we owe them. That's still the case. I mean, we're still doing reporting, even more reporting, of course. But today, basically any feature that you see or touch in our application is driven by big data, at least in the sense of A/B testing, because basically any feature that we have has been A/B tested before it hits you as a user. If we take a look at another aspect here, is we have this sense of autonomy at Spotify. So every team or squad, as we call them, but I'm using team here instead. Every team has sort of their right to decide how they work with stuff. So that also drills down to big data. So here we have team A. They have a process to produce some data set by basically consuming 2 other data sets. And it's really up to them to make this work. And then, of course, as time goes by, you get other teams that are interested in your data, and you start to get dependencies. And the dependencies, so let me backtrack. So the reason why we have autonomy is basically that we want to move as fast as possible. It's key to move fast in this industry, otherwise there's a big risk that you will die. So we have a very strong focus on time to market for our features, but also a strong focus on experimentation because we believe that we need to innovate in this space, and we do. Now this is sort of easy when you have 3 teams, 5 data sets, and as you start looking at this for real, I mean, if you look at the situation we have today. So this is a snippet of our data dependency graph. So each of these ellipses is a data job. The arrows are dependencies. And if we start zooming out, you can see it becomes fairly complex, fairly fast. And if we zoom out, I mean, we can't even see the full picture here. It almost becomes some kind of art form. And today we have more than 4,000 individual data jobs, and there's more than 13,000 dependencies here. This is a fairly complex setup now. Imagine if you're on the right-hand side there. needing some kind of report at that end, and then something breaks upchain or upstream here, it's kind of hard to tell, because over time we focused so hard on autonomy and speed that we didn't track things like ownership. How hard could it be, But in this kind of situation, it is pretty hard. So let me come back to that. And basically, this huge sort of scale and influx of data and this sort of complexity converged in 2015. So what happened in 2015? Yes, we had what we call the summer of incidents. So this was a strain of incidents that were seemingly unrelated. They were just piling up. And as you probably know, we're a Swedish company. This is Sweden in summer, and people take vacation, and typically like 5 weeks of vacation, which means it's kind of hard to get hold of people. But we set up a war room, and we started, chewing through these incidents. And but it was a struggle. Our Hadoop cluster was really on its knees. In the setup that we had back then, basically we have the big Hadoop cluster in the middle, and we have all these what's called edge nodes, basically machines, Debian machines that have access to Hadoop, and those were the ones who actually scheduled the jobs in Hadoop. And these were very basic setups. You have cron, which basically then just through command line starts your MapReduce thing, whatever framework you were using and whatnot. So every team had their own kind of sort of setup through Puppet and whatnot. Now the challenge with this was that, for instance, when we needed to restart Hadoop, because we needed to restart the name nodes, because we might, have changed the memory configuration of the VM or something, we were basically DDoSed by these scheduled jobs, because all of these edge nodes were hammering Hadoop. And typically, if you're familiar with cron, what you do in cron, you set a time when it should do something, and you tend to pick the full hour or the half hour. Now scale that times 100 or 1,000, now you have 1,000 jobs starting pretty much at the same time. The clocks are fairly synchronized, so within a few milliseconds you have 1,000 jobs trying to, and that's a nice DDoS. So we were DDoSing ourselves. Now the way we solved that was basically talking to our networking team to actually firewall off all the edge nodes and then one by one enabling them. Crude tool, but it works. But it's kind of it's not really sustainable. Our event delivery system, which we had back then, a Kafka-based system with this, it has a custom reliability and congestion control on top of it. We had trouble with it. And it was breaking, and we got it up and running again, and then you're in a catch-up situation, which basically means that your event delivery now threefolds. Now, if you're familiar with Hadoop, Hadoop runs both processing and data on the same nodes. So HDFS, which is the file system, is typically where the event delivery terminates and wants to push data. And of course, if you're tripling your load there, the processing nodes are not happy. So this was pretty bad. But we fixed it, with a bit of tweaking and a lot of manual stuff. And then we had these dependency chains, and you had things breaking, and you realized that very late in the chain, and you had to go back very high upstream to fix something. Now you have a big tree of data jobs that you actually have to reprocess. And sometimes, back in time, because you were creating these data partitions per hour, and you have to go back, say, 3 days and reprocess this, plus the whole tree. That's a fairly big thing, and you had to do this completely manual. And what they meant, you had to go and find that cron file and submit exactly that statement. It was some blah, 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 blah thing, Luigi, whatever, a command to run. Kind of a tedious thing. And also the setup with these edge nodes where you had cron typically running off Luigi, which is our sort of dependency framework thing that is just a wrapper around the actual MapReduce job that you're running, it catches the output log from your sort of main program, the submission, the submitted job. And typically, in many cases, you needed to get to that log, not the logs that were in Hadoop. There's a nice API for that. But you had, and then that meant you had to find the right edge node. You had to then go through an aggregated log. So these were all collected into a single log. But these edge nodes were used for more than one data job. So you had all of that thing in one log file. So it means that you have to filter out and try to figure out what of these are actually the log lines for that run of your job. And it was really tedious to do. So, you know, there's a lot of challenge there. But, you know, we fixed it. You know, we're pretty decent engineers, and we are tenacious, so we kept on it, and we fixed it. But that whole thing, you know, this sort of cooled down after a while when we fixed our Kafka thing by basically throwing hardware at it, you know, over-provisioning like mad. And we had some new configurations for the Hadoop, and I think we also deployed some new name node servers with a lot more memory. But after this sort of when we sort of cooled down, we started thinking, you know, how do we end up in this situation? Could we have dealt with this complexity and this ever-increasing load in some other way? So we identified a few areas where we had challenges. So, as you remember, we have these long dependency chains. So we really needed a way to get early warning when something was wrong in these dependency chains. Not when it was like done and some guy who needed a report realized that, oh, hey, the report is not done, let's go backtrack and try to figure out where the actual problem was. And this is why we built Datamon, for basic data monitoring. Debuggability and control. You heard, you know, with this Chrome edge node setup that we had, it was really hard to get to the log lines that you actually needed to understand what the hell was going on. Sorry for the profanity. And then the controlling part, like, you know, we don't want to be talking to our networking team to start firewalling off subsegments of our network every time we have some trouble. So we needed something to control this much better than just Chrome. And that's why we built sticks for scheduling and control. And the last part, with the event delivery system, we had to do a lot of manual tweaking and, you know, throwing hardware at it and basically over-provisioning like mad to actually make this thing scale to the scale that we had. I mean, this is kind of a nice problem to have, that, you know, we've ever-increasing number of users create an ever-increasing number of data. But what we realized that the complex setup or the complex tool that we had with Kafka and this custom reliability and congestion control, we didn't really, it was not really reflected very well in the capacity model that we had. We had a capacity model, which we'd sort of execute on manually. You do some basic calculation and you get some kind of number. This is the number of machines you need for the brokers and so forth. But we've hit a point where this was no longer working, and we couldn't really model it. And basically, our capacity model had failed us, and we realized that, you know, this is not the state we want to be in. We don't want to even want to bother with scale. That should be automatic. So that's why we've built a system called Gobble. So to deal with the ever sort of increasing load without us being part of that problem as engineers. So now I'm going to go through these systems and basically go through the thinking behind of these. I mean, what we did and why. So let's start with early morning and Datamon. So the summer of Incident taught us that we needed to be better at spotting errors earlier in our data. And if we take a look at one of these dependency graphs, so I've tilted it on its end. So you have your end product or the report on the top, and then you have all the dependencies that trickle down here. And when you look at this, you know, it sort of resembles an iceberg. You see only the top 10%, and that's typically what you can track, and the rest is hidden in the depth. And when you need to fix it, you have to take a deep breath and just dive deep and try to figure out what the hell is going wrong. Sorry, profanity again. Not a good thing. So how did we actually end up in this state? Well, I sort of explained it earlier. There was, our focus on autonomy and speed that really got us there. And also, sort of, from our perspective, being the data infrastructure team, we didn't really realize this was a problem until it blew up in our face. So this is just a friendly reminder to people who might be in the same kind of situation or moving into it. So we identified 3 main problems with our data when it came to data management. We didn't have a unified view when it came to data sets. We had different assumptions and different expectations on the importance of data going from consumer to producer, going from producer to the consumer. And this other one was really crucial. We were lacking a clear ownership model. It's a very simple thing, but it's something that you have to do. And you have to, I wouldn't say enforce, but you have to enable. And we never did this. So in these incidents, we had to basically go to our Git repo once we figure out what the job was, do something like a Git blame, or look at the Pehrs who was the actual submitter of this, try to figure out which team they belong to, just to find out that this person who wrote this thing has actually left the company. Now it becomes my problem. I have to fix this code. Not particularly where I want to be. The last point, SLAs, like declare what and when are you breaking your SLA. I mean, we had no way of indicating, how many hours can something be delayed, and it's still okay. We had nothing like that. Some teams actually had. I mean, they've built something on their own. They even had some alerting, but there was no unified way of doing this. So our approach to this was to create a terminology. So make sure that we all speak the same language. So what is a data set? What is a data pipeline? What kind of metadata describes data, really? And how do you express SLAs? And what does it mean in the data context? So we defined this terminology, and in data infrastructure, we started using this against our stakeholders and our customers, and really pushing it through. The other part was we needed to provide a language to express this. And the nice thing here is that at Spotify already, we have a metadata language that we use for microservices. So most backend developers are already familiar with, so basically you create these YAML files with data that describes your microservice, and we use the same mechanism. The nice thing about this is that we could reuse that whole infrastructure that we already had in place, because we have a system that we call System Z, which is basically our service registry, and it will scavenge or go through Git on a cadence to pick up these YAML files. And it picks up basically any YAML file. And that's quite nice, because then there's a REST API that Datamon then can query. So by basically declaring your data sets and your SLAs and so forth, we can now then implement what was the tool to visualize this for you. So this is a snippet of what it looks in Datamon. So from top to bottom, you have a number of data sets that you've selected. So the nice thing here, of course, is that me in a team, I can pick the data sets that I want to look at, and I can just make a monitoring page of this. I can just put it on my wall and watch this. And it's fairly clear to see that we have a problem here. There's a red dot there, which means that you're in trouble. So all of these squares, you see there's small and bigger squares. So the small squares are hourly partitions. So this is the sort of terminology that we're using. And the big ones here are daily partitions. So that's what you also express in your metadata, that you're doing something on an hourly cadence or you're doing something on a daily cadence. the red dot, the greens, of course, means that everything is okay. It's been delivered and it meets the SLA. The red means that you've broken the SLA. Typically, this is also integrated with PagerDuty. So we get a page, my phone goes off, it's 3 a.m., I can go watch this. Oh shit, something is going on. Now the blue dots there are kind of interesting because what they indicate is that there's missing dependencies. So it's been trying to schedule this, but the dependencies are missing. And what it tells is that that data set has a recursive dependency. So it depends on its previous hour. So the downstream ones can't run because the previous has not been done. And this has helped tremendously in catching data problems early. I mean, it's a fairly simple thing, but again, I wanted to share this because I'm hopeful that if you guys are in sort of a similar situation, that you really think about operational tools like this, because this is not something that you typically find off the shelf, and it's kind of hard to just integrate because it sort of have to integrate with your sort of core infrastructure. Now let's move on to debuggability and control and sticks. So from the summer of incidents, we felt like we need a better way to debug and control our job executions. And first and foremost, we need to have some kind of execution control. It was really hard to control, as you remember, firewalling off shit to just make things work. We needed a simple way to talk and interact with these jobs. So two parts of that. One is controlling on and off something, but the other thing is also talking about it. Again, we're coming back to the stuff that we did with Datamon and terminology. So we define that a data job has a name. We call it endpoint. So it has an endpoint, which is basically identifying, and also typically a partition. So a partition meaning an hourly thing or a daily thing or whatever the cadence of it has. So when you identify to run something with sticks, you talk about these two things. So what is the data set you want to do something with, and which typically like date hour you want to do it with. And then with sticks, it just becomes a fairly simple service that coordinates with our service registry to pick up stuff again. So the other part is execution information. If you're familiar with cron and you've ever debugged why your cron line doesn't work, it's pretty bad. I mean, cron doesn't really give you any feedback on, when was something run and how it actually worked. So we just had to trash that whole idea. So now Sticks is in full control of execution, and it can save into its own data store, the state of your runs. And I'm going to show that later. The last bit, execution isolation. As you remember, I talked about we had all these edge nodes. These are basic Debian servers. Nowadays, Ubuntu, sorry. But basic mechanism to control software on these is Debian packaging. And that's a great thing until you start, piling software on top of each other. Then you have one team, they want to experiment with something, so they bring in a new thing of something that is breaking backwards compatibility, and then now you're in dependency hell. So, as the byline says here, Docker to the rescue. I mean, we changed the model to, instead of doing the edge node thing, we said anything that we're going to schedule in our data infrastructure is going to be a Docker container. So the submitted job is actually maintained in its own sort of bubble. If you take a look at the execution control, so this is sort of what it looks like in, Sticks is not a GUI system at all. Sticks is just a REST API on this execution engine. So this is actually part of our service registry system set. So there you can easily just turn on and off stuff. And because this is also a REST API, it's easy scripted. You could actually just use curl against Sticks to do these things. But we also have, you can't see it here, but we have a command line tool that simplifies it, because then you can just focus on the data set identity and the partition that you want to do something with. And there you can then rerun, re-trigger stuff. You can actually look at the data as you do. But we also have the execution information. As you remember, I talked about cron not having a lot of information. Now, what Styx does, it will collect data about your executions. And again, this is a visualization from system-Z. And again, this is just an underlying REST API that sort of is queried here. And so from top to bottom, you have the different partitions that we've been trying to produce here for a particular data set. And then left to right, you have the executions that have been tried by Styx. And we've selected one here, so it's been expanded, and you can see that it first time it was missing its dependencies. Next time it failed, it had an error, and the third time it actually succeeded. Now, I'm interested in what happened there with the red one. And now what I can do is I can just click on it and I will see the logs, and just the logs for that execution. So this became a fairly simple task, because with our Docker containers, we could just easily now tie them into Google Cloud Logging. So we didn't build anything of this. This is just a Google service that we used. Fairly simple integration. But the real benefit for us, of course, is that with one single click, I can see the details of the submitted job, where I typically could see what the problem was. And the last part is execution isolation. As I mentioned, we're using Docker. The interesting part here is that we're using Kubernetes and the Google Compute Engine. So basically, that's really what Styx is sort of a layer on top of. It will take your metadata, figure out which Docker container to actually start, and then just use this cluster to do it. And the interesting part about Google Compute Engine is with the instance groups, you can define auto-scaling. So you don't have to beforehand decide this is going to be a 200-node cluster. You just tell it what the boundaries are. We're always going to run like 4, and the maximum is 1,000. And because these jobs are typically not scheduled evenly. You don't have an even load of jobs. They do vary over time. But what Styx also does, it doesn't now schedule things on the hour, so we don't get those spikes anymore. Because sometimes these Docker containers are running inside of Google, like the actual MapReduce thing is inside Google's MapReduce, and sometimes, which is more common now because we haven't transitioned everything, they're actually scheduled in our on-prem Hadoop cluster. And there it's much more sensitive to like these spikes. But that's now Styx sort of, it takes care of making sure that we don't overwhelm our on-prem cluster. And I mean, myself, I love this fact that I can pinpoint and go and see what exactly happened to my data job. Because I was there back then debugging this. It was not fun. The last bit. So let's take a look at how we were able to automate capacity with our event delivery system. So let's take a look at Gobble. So back in 2015, we had this complex setup with Kafka. And this is a very old, we started with Kafka pretty early on. So this was based on Kafka 0.7. It was old back in 2015 already. And Kafka 0.7 doesn't have reliability, so we built this reliability layer on top, but we also built a congestion control thing on top because historically before, we had problems with situation where we overwhelmed HDFS. And as you remember, HDFS is the data store for Hadoop, and it's shared with the processing nodes, which means that if you're overwhelming your Hadoop HDFS layer, you're also overwhelming your computing power. Kind of a bad thing, but so we needed some way to make sure that we're not overwhelming that layer. Now this became a fairly complex setup, and as I mentioned before, in order to make this work with this sort of ever-increasing scale, we had a capacity model written down on paper, and we needed to go back on and basically execute on it. But at a certain point, like in 2015, it just broke because this congestion control thing was kind of hard to model. And this is really where we started feeling that we need something that basically can take us as engineers out of that equation. So we can just make this happen, so we can focus on other stuff. So at the time, we were looking actually at, or we had actually started working with Kafka 0.8 because that's, next version of the system, has reliability. Congestion control was still sort of a challenge there. But we had also started to talk to Google. And in our talks with Google, there was 2 products that really stand out. And that was PubSub and data flow streaming. So looking at these 2 products, with PubSub, we could just replace that whole Kafka thing. It's a very similar kind of construct. Both of these, both Kafka and PubSub, have this at least once delivery semantics. And what that means is that on your consuming end, when you end up storing something at the other end, you're going to have duplicates. Now that's a bit of a problem if you're counting stuff, because you want typically sort of as accurate as possible, or only once delivery, exactly once. So typically at the end of it, and that's what we had with our old pipeline, you have something that can deduplicate this data. It's typically a MapReduce job or something. But what we found out with talking to the data flow team was that with data flow streaming, we could just create one simple program that could do this on the fly for us, and then just put it in GCS, in storage. Sounds perfect, right? So we're done, right? Just, because also data flow streaming has this, it's a offering from Google that actually scales automatically. So yeah, we have all our scale now. But do you believe what your solution providers say about their products? Yeah, I wouldn't think so. Neither did we. I mean, it's Google. We kind of trust them. They're cool. They know typically what they do. But we just want to make sure, because we've been bitten on, in our ass before by, believing stuff. So we really wanted to make sure that these could handle this load. So we started pressure testing PubSub. And we wanted to make sure that this just didn't handle the sort of peak load that we have at the time, which was basically 500,000 messages per second. We want to make sure that it did at least tenfold of that, because then we were at least a few years away, hopefully. So we want to just make certain. So with PubSub, we did some simple tooling and just started pressuring the hell out of PubSub. And it worked really well. PubSub actually performed quite well, and yeah, basically could swallow anything we threw at it. Sometimes with a bit of hiccups, but generally not a problem. And the hiccups were typically on our side, but typically being PubSub and topics, it actually solved itself out. Now, then we moved on to data flow streaming. So we looked at this, and we ended up writing a fairly simple program, about 2,000 lines of code, of Java code. And we started testing this, and it worked fine to begin with. But then, we wanted to really pressure this, so we started, let's just turn on the faucet and just dump everything in there. We took some of our bigger data sets and just put it in there, so it's bigger events. And then we started to get trouble. It would crash. We got into weird corner cases. And we were hit basically by that the construct in data flow streaming is that they do windowing in memory. So this now becomes a problem of a sharding problem. So this happens automatically under the hood for you, but this also means that if your load sort of fluctuates, you might be breaking this because the thing that you're trying to dedup just couldn't fit into memory. And there was no good way of, in data flow streaming, to actually redo stuff like that. Yeah. So, and eventually we just realized that, we were just, our use case didn't really fit the data flow streaming. On a theory, yes, but in practice, just couldn't really work. And we were just, expecting a bit too much out of data flow streaming. It works well when your sort of data is moderate, and that's really what it's built for. It might have been changed over time now, but we basically realized after a while, after spending some time with this, that we have to backtrack here. I mean, data for streaming is not for us. So we ended up going back to building a more traditional approach, a few microservices, MapReduce job. So the microservice is basically just pulling data out of PubSub, putting it in some intermediary store. We have another service to keep track of what's going on, and then we have a MapReduce job to actually do the dedupping. So typically what we do is we have hourly partitions. So the MapReduce runs for a certain event type for a certain hour and produces that. Now, nice, right? But now we're sort of back to the problem again. So if we focus here on like the consumers here. Now these are microservices that we need to scale in order to actually handle this load and the fluctuation load here. So that's kind of bad because this is what we wanted to get out of. And that's where, again, like I mentioned with Sticks, we found Google Cloud Compute Engine autoscaling. So by basically creating instance group where we could set a lower and upper boundary, we can now get these consumers to scale automatically with the load. So we're not over provisioning, but it also will follow whatever to a certain extent. I mean, we still have to cap it at some point. There might be a bug in there or something, but it basically flows with the load. That's nice. Now, what we realized also was that the ever-increasing load was not just from getting more and more users. It was also coming from the fact that we had more and more teams wanting to use our platform. And we realize now that the bottleneck here for scaling is us as engineers. Because configuring this now, to make this happen, you need to set up a topic, you still need to set up that instance group with that sort of elasticity. So now we are the bottleneck. And that's why we built a fairly simple construct called the stuffer. And again, this works on a sort of similar pattern with the Sticks and with Datamon, that what we did was we require our services to declare yet another metadata file in a YAML file that we can collect from our service registry, where you describe what is the event that you're producing. And that's it. It's a very simple thing. It's just basically an identifier. But what we do with the stuffer is basically we set up that topic for you, we set up the consuming end for you, and you get your own cluster to do this. And then voila, it gets into GCS storage. And we also provide, so it actually gets into BigQuery, but that's a sort of another story. And of course, these components are scheduled with Sticks, and we monitor them, like the data flow, the MapReduce thing, we monitor that to Datamon. And that's a very nice sort of marriage here. Now, let me summarize. So this is a bit sort of all over the place, but the main sort of thing that I want you to take away from this is two things. One is about operational tools or operational situation for your big data. I mean, there's basically nothing out there when it comes to operational tools for big data. When it comes to development, there's tons of frameworks, there's tons of tools to do this, but when it comes to operation and quality of your data, there's really nothing, unless you buy a fully packaged deal, I guess. I haven't really looked into that, but we are really not about that. We want to have small and manageable components. So my point here is that, if you're venturing into this, if you're sort of at the point where you're starting to scale, just think about these things and think about how you track these things. And make sure that you keep track. And I would say visualization is a key here. And also like the SLA part, like people actually manning up and owning things, because that has been a big change for us. And when it comes to capacity, remember your capacity model might be wrong. It might blow up. So the simple answer here is, try to automate yourself out of it if you can, like we did. I know it's not possible everywhere, but if you're lucky, like us, and having sort of a scalability issue because of, ever-increasing load, at some point you are going to need to automate. There's no way you can, because otherwise you start scaling up the number of people that needs to deal with this, and that's just not going to work. Because what happens is that you're just going to try and do more with less people, and you're going to stress people out, and then they're going to start quitting on you, and then, not a good thing. And that's it. Thank you. All right. Do we have time for questions?
We do have time for questions.
So anybody wants a question, there's a microphone over there. You have to walk up to it. Or if you shout out, or you can come just down and talk to me if you have questions. I'm here. I'm staying for the party, man.
Yeah.
So
maybe we take...
There's free beer.
Yeah.
No,
we'll
not
take questions after us then. Okay,
all right, thanks.